Hey guys, it's Miss Marfleck here. We're going to go through a review of the functions packet. Now we've done most of this before spring break, so you might want to, go back and take a look at some old videos or notes to kind of refresh your memory. Keeping in mind that the assessment or the short quiz that we're going to be taking will be multiple choice, but we're still going to go through each and every topic, first starting off with interval notation, then we're going to take a look at our piecewise functions, we're going to do domain, range, intervals of increasing, decreasing, constant, domain algebraically, and our even and odd functions. All right, so we're starting off with our first Roman numeral here. I'm going to upload this, but you're going to see that we're going to skip around a little bit because I want to do it in the order that I taught the content. Starting off first here's our quick notes for our interval notation. If you can recall, we used a bracket when we were inclusive, we used a parentheses when we were exclusive, we used a U to denote the joining of two sets, and we always use parentheses with our infinities, and then we always ordered from least to greatest. So starting off here with number 1, write our inequality in interval notation. Well, x is less than or equal to -4 or can be greater than 7. First, starting off with our left piece, because that's the smallest, we come from negative infinity and we can go all the way up and include -4. Or we have this extra set, joining this set with the union, our x can be greater than 7 but can't be equal to 7. So there's all of our values greater than 7. Taking a look at number 1, letter B, here are our endpoints. X is between 1 and 3, but it can be 3. So there's our endpoints in our interval notation. It can't be 1, but it can be 3. And then now in number 2, we're given a graph, and now we have to give the interval notation. So we come from negative infinity, and we go all the way to -1, and we're inclusive of -1, and then we pick up again at 3, exclusive, and we go all the way to infinity. Taking a look at letter B, we're from -6 to -2, we're inclusive of -6, and we're exclusive of 2. All right, so now would be a very, very good time to pause the video and make sure you have all of this down. Okay, moving on. Now we're going to take a look at our piecewise functions. So we're going to start off here with number 2. I'm going to switch from pen to pencil because sometimes I make a little mistake, maybe with a value or the way I graphed it, didn't count right, whatever. So switching to pencil here, and there's our quick notes for our piecewise function. It's really helpful to use a table of values. I'm going to graph these without a table of values though, because most of them are linear equations or constants, and we know what the functions look like. And then just keeping in mind that our function, which is our y values, are on the left hand side, and that our domain or our restrictions is on the right hand side, and this is going to be our x values. Now whether or not we include the number, you still have to graph it. That's a common misconception I've been seeing in your work. You're going to be graphing definitely x equals 1 here. You're just going to be using an open circle. All right, so we're going to start off. I like to always begin, let me see if I could, there we go. I like to always begin by first putting, what circle I'm going to use. So, this is going to be inclusive, exclusive, and then inclusive, exclusive, and then inclusive, and then this is going to be an exclusive. First, starting off with this top piece, this says for all the values of x that is less than or equal to 1. So here I am at 1. My y value will be 1. So all of my y values are going to be 1 when all the x's are less than or equal to 1. And that goes on and on forever. All right, so we did that first piece there. And then now from 1 to 3, we have this linear equation of a slope of 1 and an intercept of 0. So we have an intercept of 0 and a slope of 1. So our first point is going to be here, and it's going to be an open circle. But then I keep climbing, and I'm going to do this all the way until x is equal to 1, 2, 3. And then at the 3, we are inclusive, so we're going to have a filled in circle there. And there's my linear equation. Now what you could have done is you could have taken 1 and plug it into the function. I got 1. You could take 2, plug it into the function. I got 2, 2. And you could have taken 3, plugged it into the function. You got 3, 3. All right, now we're moving on to this third piece here. We have an intercept at 6, so 1, 2, 3, 4, 5, 6, and we have this downward slope of -1. So we're here, and then when our graph is at 3, we have an open circle, and we're going to do these x values all the way until we hit x is 6. So this would be at 4, this would be at 5, and this would be at 6, and at 6 we have a filled in circle. All right, so once again, this has an intercept of 6, and it has a slope of -1. And then for this last one, here, when x is greater than 6 or 6 is less than x, we always have these y values of 0. Now we're gonna have an open circle here, but there's already a filled in circle, so then I can just fill in all of these y values of 0. If you don't like that, do the method that we did, in our previous video. It's a little easier, it takes a little longer, but use a table of values and plug in values. All right, and then now we're just going to do some quick evaluating. When x is 2, this is just showing me, you can read notation. When x is 2, f of 2, which is our y value. Let's see, when x is 2, our y value is 2. All right, and then here when x is 7, our y value is 0. And then when f is -20, it'll be way out here, our y value is still going to be 1. You could have also used these restrictions up top. All right, so there's the first one. And then now we're going to be taking a look at this piecewise function over here on the right. All right, once again, starting with those circles, this is inclusive, this is exclusive, and then inclusive, and then this is exclusive. Okay, for the first one, where all of our x's are less than 0, we have this linear equation which has an intercept at -1 here, and then it has a positive slope. Which means I'm going to be going down and left, down and left, down and left, okay, because this is negative, negative becomes a positive, that slope. And then you could see here that we're going to have that positive slope there, and all the way to when x is 0. So all those x values less than 0. All right, and then now when we're going from 0 to 5, we have that intercept still at -1, open circle, but this is already filled in, so I don't have to write the open circle. And then now I have a slope of 2 all the way to x is 5. So I have slope of 2, that's x is 1, slope of 2, that's x is 2, slope of 2, x is 3, slope of 2, x is 4, and then slope of 2, we're a little bit off the chart there, that's x is 5. So you could see that this will have a little bit of a steeper slope, but still has the same intercept. And then now we have an open circle. When x is 5, 1, 2, 3, 4, 5, our y value is 3, 1, 2, 3. And then that's going to go for any x value that is greater than 5. All right, and then now we're checking our graph or our piecewise function up here, and when x is -2, our y value is 1, 2, 3, -3. When x is 0, our y value is -1, and then here, when it is 5, 1, 2, 3, 4, 5, you have to go to your filled in circle, not your open circle. This is undefined here, and that's going to be 9 way up there. All right, so that's it for our piecewise functions. And then now we're going to take a look at our next topic. This is a good time to kind of pause the video, make sure you have all this. And our next topic was domain, range, intervals of increasing, decreasing, and constant. I'll come back to the sheet in a minute. All right, here's just our quick sticky notes for the next topic. With our domain, range, intervals of increasing, decreasing, and constant. Domain and range, domain is your x value, range is your y value. With domain and range, you can use a bracket. Now, you're only going to be using a bracket, when you have that filled in circle, but you can use it. And then now the increasing, we have that positive slope, decreasing, we have the negative slope, and constant has that flat line. And with increasing, decreasing, constant, you're always using the x values, and no matter whether it's an open circle or closed circle, you are always using parentheses, keeping in mind that those definitions are defined on an open interval. And then you're going to have to read from left to right. All right, we're starting off with, letter A here, and we're looking at that fx graph, and we're trying to figure out the domain. So the domain is, we're going to start off with our lowest x value, and that's going to be here at -6. All right, and then you could see it's an open circle, and then our we define from -6 all the way to when x is -2. All right, and it's an open circle. And then we're not defined at x equals -1, 0, 1, and then we are defined here when x is equal to, let's see, is this a line here? Yes, it is. 1, 2, and we're inclusive of 2, and then we go all the way out to infinity. So there's a, a prime example that we can use a bracket with domain. All right, and then now taking a look at our range. Our lowest y value is 0, and it's not inclusive. And then we go all the way up to our highest y value, which is 5 here, and that's also not inclusive. Now it's time for intervals of increasing, decreasing constant, where we're always going to have parentheses no matter what, and we're looking at those x values. There's no interval where we are increasing. We don't have any positive slopes here, but we do have this decreasing segment, and it's decreasing from the x value -6 all the way to the x value -2. And then now we have this interval of constant here, and that's going to be from 2 all the way to infinity. Notice how I'm using a parentheses at 2, a parentheses at 2. All right, now looking at letter B, we're going to be using this g of x graph, trying to figure out that domain. This, our lowest x value is coming from here, which is going to be -infinity, and then we're going all the way, and we're stopping at 0, and 0 is inclusive there. And then we go from 0, and then our graph picks up again at 1, 2, and this is going to be 3, where it's an open circle, and our x values go all the way out with that arrow to infinity. Now it's time for our range, and our lowest y value is going to be inclusive of 0 right here, and then we go all the way up, 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 and then this graph takes us all the way up to infinity. Now it's time for intervals of increasing, decreasing constant, where no matter what, we are using a parentheses. We do have an increasing segment right here, and that's going to be increasing from the x value 3 all the way to the x value infinity. We have a decreasing segment here. We're going to have to count to see what this is. 1, 2, 3, looks like 4, parentheses from -4 all the way to 0, and we have a parentheses again. And then we have this segment that's constant all the way from the -infinity to this x value -4. All right, so once again, that's our last piece of notes there. If you want, pause the video, make sure you have these notes from the sticky note for our domain, range, increasing, decreasing, and constant. All right, after we did domain, range, increasing, decreasing, and constant, the next thing that we did was domain algebraically. And with domain algebraically, we really only had 3 quote unquote rules, and that was for polynomials, which was always from -infinity to +infinity. When we had a denominator, the denominator could not be equal to 0, so we omit those values that made it equal to 0. And then for any even roots or even radicals, everything underneath the radical must be positive, so we set everything underneath the radical greater than or equal to 0. And those were our 3 rules. Okay, now we're taking a look here at letter A. You can see that this is a polynomial, no denominator, no radical. Our domain is from -infinity to +infinity. Taking a look at letter B, we have a radical, so we have to take everything under the radical and set it greater than or equal to 0. Now, I'm not worried about the +1 on the outside because it's not equal, or it's not under the radical, so it's not going to affect whether the radical is positive or negative. So we need everything under here to be positive because we can't take a negative root, we get an imaginary number. And then we're just going to have to solve, for x here by adding 5, by dividing by 2, and then we're seeing here that x has to be greater than or equal to 5 over 2. So we have 5 over 2 inclusive, and then we go all the way out to infinity. There's that interval notation that I'm asking for in the directions. All right, now taking a look at letter C, we have 2 things going on here. We have a radical up in the numerator. We got to make sure that that radical is greater than or equal to 0, everything under it. And then we have this quadratic down in the denominator. So we're going to go ahead and we're going to factor this quadratic and see what values is going to make it 0. So we're looking for those 2 numbers that add up to, let's see here, that add up to 9 and are going to multiply to a -36. And that's going to be a +12 and a -3. And then you can see that they multiply to -36 and they add to a +9. And those values cannot be 0. So we have x cannot be -12 and x cannot be a +3. And then we also have to combine that, with this inequality that x is greater than or equal to 0. Now, Ms. Cushman sent me her answer key, and I really like how she did this graph, and I didn't do it in the video, but I see that she kind of sketches it out to kind of help maybe visualize. So we have this first one where x has to be greater than 0. And then we have these values where it can't be 3, so we have an open circle at 3, and it can't be negative 12, open circle at negative 12. Now you can see that the negative 12 is not going to affect us, so we start at 0, and we go all the way. We have to omit the value 3, and then omit the value 3, and we can go all the way up to infinity. So that's a combination of these two from the numerator and from the denominator. All right, so it gets a little harder once you keep adding in more and more rules. Instead of doing 1, maybe we're doing 2 or 3 here. All right, taking a look at letter D, we're really just focused, no radical in the numerator. We're just focused on factoring that denominator there. And we're going to go ahead and we're going to look for our two values that multiplied to 8 and are going to add to 6, and that's 4 and 2. And those values cannot be equal to 0, so we have x cannot be negative 4, and it cannot be negative 2. Now, even though you may be able to remove this discontinuity, it does not matter. A removable discontinuity will still make our function undefined. So I can't just cross out the thing in the numerator and the denominator and say, okay, that's it. No, even though it's removable, okay, it's still going to be a discontinuity. So here we start from negative infinity, omitting the negative 4 first, omitting the negative 2, and then going from negative 2 all the way to infinity. All right, taking a look at letter E, we have two things in play here. We have our radical, which has to be greater than or equal to 0, and then it's in the denominator, so it cannot be equal to 0. So we're going to have this inequality now where we're just greater than 0. We did do one like this in our last video, or the video before that, when we took a look at domain algebraically. So once again, we would do greater than or equal to 0 for the radical, but now since it's in the denominator, it can't be equal to 0, so it's just greater than 0. And then we have x here has to be greater than negative 4 when I subtract 4 from both sides, and we have an open parentheses, and all the x values are greater than negative 4. And then for this last one here for f, we just have negative infinity all the way to positive infinity because it is a polynomial, no radicals, and no denominators. Now would be a good time to just kind of pause, make sure you have, I'll put it over here maybe so I don't block every single problem. Just make sure you have all this down. All right, you've made it. We are doing the very last topic that we did together, and that was even and odd functions. All right, even and odd functions, our notes are right here. I did upload a graphic organizer in our last lesson that went over, when you plug in negative x, that's how you solve for both even and odd. If you get out the same function you started with, it's an even function. If you get out the same function you started with and it's multiplied by negative 1, it is an odd function, and then if it's not even or odd, we say it's neither. Even functions with graphs are symmetric to the y-axis, and odd functions are symmetric with the origin. All right, now we're taking a look at the left-hand side of this paper, and we're going to take a look at letter, we'll call this, this is graph A. Perfect, graph A. Graph A is going to be an odd function because it has symmetry around the origin. You can tell because it has, the function in that diagonal quadrant, or we talked about how you can fold it over the x-axis and then over the y-axis, and you should get the same function. Or you can think of it as a 180-degree rotation. Or you could pick a point, like let's say, this is 1, 1. When I use that definition of even and odd, which I'll put, right here, for an even function, if I make the x negative, the y stays the same. So I'd be here at negative 1, positive 1. But with the odd function, when I make the x negative, the y also changes value. So if I'm here at negative 1, 1, and both coordinates change signs, then it is an odd function. Taking a look at letter B, it may be a little tempting to say that it's even because it does have some symmetry, but it's not symmetric over the y-axis. And it also doesn't have symmetry around the origin, so this is an example of a neither graph. And then taking a look at C, you guessed it, C would be even because it's symmetric over the y-axis. So there's a good example of all three graphs. Now we're moving on to the right-hand side of the page, and this is where I think things get a little more tricky, is when you're working with the algebra. But every problem starts off the same way, by taking out the x and replacing it with a negative x. Once you replace it with a negative x, you have to look, is my power even or odd, okay? And that'll affect my signs. Since this is even, negative raised to an even power will become positive. This is odd, it'll stay negative, so this sign switches. This is even, okay, which means it'll become positive, and then you have that negative 1. All right, now you can definitely see that this is not the function we started out with because it has a different sign here. All right, and then it's also not this whole function multiplied by -1 because then I'd have negative x to the fourth plus x, 2x cubed minus x squared plus 1. And that's not what I have here. So it's neither even nor odd. So this is going to be an example of a neither graph. And then if you just want to double check, it's usually harder to identify the odd. If you don't believe me, you could take this whole thing and just multiply it by a -1. Make sure it distributes to each and every term. All right, now taking a look at letter B, doing the same thing, starting off with the original function, taking out the x and replacing it with a negative x. So we have 2 negative x to the fourth plus negative x squared, a -1, and then I'm just extending that radical here. All right, and then we're going to do some simplifying. This is negative x, and then x to the fourth will be positive, x squared will be positive, and then we still have that -1. Now you can definitely see that it's not even because it's not the exact same graph. However, this is an odd function because if I took, my original, we're testing for odd, if I took my original and multiplied it by -1, this is what I would get. Keeping in mind that this is one term here, okay, because it's joined with multiplication. So that -1 would just go in front here with the x. All right, taking a look at letter C, we're almost done here. Taking out our, maybe instead of having y, I should have put f of x, all right, but it doesn't matter. Taking out the x and putting in negative x plus 1, doing some simplifying. Well, any negative inside will become positive. So I'm going to put positive x here, and it's going to be our original function, and that is even. Now, if you don't believe me, just think about the graph, okay? Think about, that this is an absolute value graph that has been translated up 1 unit. It has symmetry over the y-axis. All right, and then the last one is D. I'm not going to lie, I do think that the denominator ones are a little tricky because when you're testing for the odd, the negative can either go in the numerator or the denominator, but it can't go in both. All right, but we'll see that in a minute. We're going to take out the x, and we're going to replace it with a negative x. Doing that both in our numerator and in our denominator. All right, and then now it's time for some simplifying. This is to an odd power, so it'll become negative. This is to an odd power, so it's going to switch that sign. However, in the denominator, this is to an even power, so it's going to be positive. Then we have that -1. All right, I can definitely see that it is not even because we don't have the same numerator. Oh, did I go off the page? Yes, I did. Okay. I can definitely see that it is not even because I don't have the same function, but it is indeed odd. When I try to multiply this by -1, that -1 can either go in the numerator, where you'll have -5x to the fifth plus 3x cubed, or in the denominator. It does not go in both. If I multiply the numerator and denominator by -1, I'm just multiplying by 1. So I put this into the numerator, and then this is my odd function. And then you can always double check on Desmos, maybe plug this function in and see if it has symmetry over the over the origin. All right. So, we went really quickly, or I think I went really quickly, even though 20 minutes is not that quick, through the video. But we did look at some sticky notes that I made for us, and I'm just going to finish off this video here by putting them all, in for all of us to see. We did our interval notation, which was this one. We did our interval notation. We did our piecewise functions. What did we do next? We did domain and range, integrals of increasing, decreasing, constant, domain algebraically, and even and odd. All right, so there is all of our notes. I will try to hold them all down. You can pause the video. Make sure you have all that. Make sure you are studying and looking back through the videos from before spring break.